Okay, very good. So let's start with the last talk of the morning session, who is going to be given by Professor Ha from Seoul National University. And he's going to talk about second order consensus models with a bonding force. Thank you.
Okay, so thank you for kind invitation. Also, thank you for kind introduction. So today, I'm going to talk about the second order consensus model. So here is brief outline of my short lecture. I'll talk about three topics. The first is the ubiquity of first order consensus models. And then I'll talk about the weak coupling of low rank tensor models. So I'll tell you how to couple different aggregation consensus models. And then the last one is the second order consensus model with a bonding force. Okay, so the first episode is the ubiquity of first order consensus models. So here, I just wrote down the first order consensus model. Qi is a state of some ice particle, some quantifiable state, which lives in some manifold M, which is embedded in Euclidean space. The psi I call just coupling function. And then the collective behaviors of biological system. So in the morning, we already seen lots of effect for the aggregation of bacteria. And also, as you can see from outside, there's a flocking of birds and the synchronization of fireflies. All these three collective behaviors can be understood as a consensus formation in position. For example, aggregation is a consensus in position. The flocking is a consensus in the velocity. And the synchronization is consensus in the phase and the frequency. So all three different collective dynamics can be understood as a consensus phenomena. At the PD level, all these three consensus models are described by different types of PDEs. For example, in the Professor Patam's talk, we already seen this elliptic parabolic coupled system, namely the Keller-Ziegler model. This is the simplest one. And also the for the hydrodynamic Cucker-Smale model, which is given by this hyperbolic the pressureless gas dynamics with the non-local forcing term here. And also for the synchronization, there is a model called the continuum Kuramoto model. You can view this as a conservation law with the non-local forcing, non-local flux. So at PD level, this aggregation, flocking, and synchronization are often described by different types of PDEs. But if you look at these three different phenomena from the particle viewpoint, for example, if you turn off the noise in the Keller-Ziegler model, then at the particle level in R3, the position of bacteria is described by these first order systems. Here, if you just replace this velocity by acceleration, which means the second derivative of xi, this is exactly Newton's n-body system. So, but the Cucker-Smale model for flocking, for example, xi is the position, vi is the velocity, then the first equation is simply the time derivative position is the velocity. This one, mass times acceleration, is given by this internal forcing, flocking forcing, I call it. And the Kuramoto model for synchronization, here theta I is the phase of some oscillatory particle object. So the phase velocity, which means the frequency, is given by the natural frequency plus the interaction, phase interaction term. So, of course, still, because this model and this model are the first order system for position, but the Cucker-Smale model is the second order for position. Therefore, in order to compare these three systems, either you lift this first order to the second order by taking time derivative, or you need to reduce the second order model to the first one. So we take the second approach in 1D, for example, on the real line. This is on the real line. Fortunately, this flocking forcing term can be written as a time derivative of this integral. Okay. So in 1D, the right-hand side is the time derivative of capital psi. Okay. So this is the time derivative of psi cs. Therefore, we can integrate the second equation, the velocity equation, with respect to t. Then you get this first order system. Here, the initial data is affect the velocity. Okay, so the natural velocity depends on the initial data and this coupling antiderivative of coupling function psi. Therefore, at the particle level, the deterministic Keller-Zeigler model and the Cucker-Smale model and Kuramoto model takes the same form as consensus model. The only difference is the state and the coupling function psi. For example, in R3, the Keller-Zeigler model in R3, this coupling function is given by this Newton force. For Cucker-Smale model, that's the antiderivative of the communication wave function psi. So this guy is a monotone increasing, but this guy is a singular at q equals 0. This guy is a periodic function. So other than the different form of this coupling function and the physical meaning or biological meaning of qi, they takes the same consensus form. Okay, so here is the summary of the first part. Some collective behavior of many-body systems can be described by this first-order consensus model. So, for example, the simplest form of deterministic Keller-Zeigler model on R3 and one the Cucker-Smale model or Kuramoto synchronization model, they can be described by this simple form. So there is, therefore, there is some hidden relations between for example, the Cucker-Smale flocking and the Kuramoto synchronization. So if you know some phenomena in Kuramoto side, there might some possibility you can find the similar phenomena in 1D Cucker-Smale thing, and vice versa. Now, you might ask, why consensus model? Why consensus model? For example, if you have say drones, or if you have these robots, moving robots, then we often want to control. We want to make some pattern formation for this a group of drones. Okay, so this consensus model can be used to the decentralized control protocol from control theory. By using this consensus model, there's some work for optimal control and the mean field optimal controls by Benedetto Piccoli and Massimo Bonazzi group. So the second thing is the CBO algorithm. So this consensus model can be used in the optimization algorithm. So this is one of the optimization algorithm, CBO algorithm. So xi sub t, that's the sample point of your sample point. So this part of this stochastic algorithm, you can see the this consensus part. Here, omega sub k is the weight. Here, L is the object function that you are looking for, to be minimized. So this CBO algorithm was done recently, was done by many people. For example, one of our speaker Friday, Professor Tochek and Jose Carrillo and other people contribute a lot on this CBO algorithm. So the main idea is that you just you're using a global particle to find the local to find global minimizer. So this is the last green cost function. The minimum is the origin. So as time goes on, this is a time t equals 0, t equals 2, t equals 10. Sorry, time t equals 2, t equals 10, t equals 50. You see that the particle aggregate to the your global minimizer, minimum point origin. So probably I think Professor Claudia Tochek will talk about in detail about this CBO algorithm this Friday. And also this consensus model has been used to the modeling of systemic risk in financial market. So if Xi is the state of risk of agent I at time t, then through this consensus model, the risk of each individual agent become decreasing. On the other hand, the global systemic risk will increase. So if you are interested in this systemic risk, there's a good reference for that by George Papanikolaou and his collaborators. And also this consensus model can be modeled for power grid. So if theta I, we have a bunch of network, we have a network, each vertex you have a generator, then the theta I is the rotor angle of the ice generator, then this Kuramoto-like system can be used to model the power grid. So there is some related reference by Doppler and Bülow and Jujun Lee and Zhao. Okay, so let me move to the second episode. That's the weak coupling of lower tensor models. So the question is, we have a bunch of consensus models like Cucker-Smale model and Kuramoto model and other models. The question is how to couple these different models so that the resulting consensus model still can exhibit collective dynamics. Okay, so before I introduce the tensor model, let me just briefly tell you what is the tensor. Tensor is a multi-dimensional array of complex numbers. For example, the scalar is the rank 0 tensor. Vector is the rank 1 tensor. Here, rank means is the number of index. So the matrix, you need the 2 index to represent matrix. So it's a rank 2 tensor here. So this guy is a rank 3 tensors. So each section is a rank 2 tensors. So in order to describe this this mathematical object, you need the 3 index, I, J, K. Okay. So for special case, for low rank case, for example, rank 0 case, which is the number, just a complex number. Rank 1 tensor is the matrix, complex, just complex vector. Rank 2 is the complex matrix case. There are some hierarchy of lower tensor models. So the Kuramoto model is the lower model for rank 0 tensors. The swarm sphere model, that's the consensus model on the sphere. Okay, that's the lower tensor model for rank 1 tensors. The lower matrix model is the lower tensor model for rank 2 tensors. Here, UI is the D by D unitary matrix. HI is the D by D Hermitian matrix. So this lower matrix model describes the evolution of this, time evolution of this unitary matrix. Fortunately, for some special case, this lower matrix model can be reduced to the swarm sphere model. For example, D equals 2. Okay. And these two models, also D equals 1, can be reduced to the Kuramoto model. So in that sense, the swarm sphere model and lower matrix model can be understood as a more higher dimensional generalization of Kuramoto model. Okay. Now, as an application of this lower tensor models, let me tell you the one application, namely dynamic chain matching for a homogeneous ensemble. For example, let's think of we have a bunch of triangles, congruent triangles, and then each triangle, let's assume that each triangle move via the rigid body motion. Okay, so the triangle stay as the same triangle along the dynamic process. The purpose is that dynamically, I want to make them overlap completely, dynamic sense. So let me say lambda is the fixed index of vertex for the reference M polytope. For example, the triangle case is we have 3 vertex, say 1, 2, 3, and xi alpha is the position of alpha's vertex of i's polytope. Then let me denote the xi bar. That's the central mass of this vertex position. Okay, central mass. Then Ri alpha is the deviation from the central mass. Okay, because we are considering the same congruent M polytope. Each polytope is congruent. That means you have if you have a reference reference state, then the other one is determined by this orthogonal matrix.
Professor Ha, can you hear me?
Yeah.
Sorry, can you stop 1 second because we're having technical problems. We cannot see your slides anymore. So
Okay.
let me just get somebody from IT and I will let you know once we fix it. Sorry about that. Sorry.
Okay, sorry.
Thank you.
영상은 이 슬라이드 맞습니다.
다음에.
특히 와이파이가 안 되네.
그러니까 우리나라가 얼마나 하이텍인 줄 알겠지?
여기서 봐야 될까?
뭐 소리?
Thank you for waiting. Now it's fixed, so please go ahead. Thank you.
Okay, so I'm not sure. Do I need to go back or just stay on?
You can stay on because I stopped you immediately. Okay, thank you.
Okay, thank you. Okay, so we are considering a bunch of n polytope, congruent n polytope. We want to make the shape matching. So eventually, the dynamic quantity will be determined by this central mass and this orthogonal matrix OI. So here is the our dynamic system for shape matching. So the this consensus model for central mass, and this Loewe matrix model, second order Loewe matrix model for a rotation matrix. So once you solve this dynamic system, then you can have a shape matching. So let me show you some video for that. Okay. Yeah. So you see that this is a bunch of tetrahedrons. Eventually, let me show you once more. Okay. Okay, so you can do a bunch of lines, triangles, and etc. So as long as you have the congruent and polytope randomly scattered, then by using this dynamic process, you can have a shape matching. Okay. Now, let's suppose we have a bunch of heterogeneous tensor ensembles. So for example, you can see rank 0 tensors, you can see rank 2 tensors, with different size, rank 1 tensors, rank 3 tensors, etc. Let's suppose we have a bunch of heterogeneous tensor ensemble. So the question is how to segregate a mixture of tensors into homogeneous tensor ensemble with the same size and same rank. Okay, so it's kind of a classification problem for this mixed tensor ensemble. So the question is how can we do this dynamically by using consensus models? So in order to address those segregation problem, eventually we have to study the coupling of two different swarm sphere models. So this is an aggregation model on this sphere. This is aggregation models on different sphere. So here, D1 different from D2. So we have two spheres each sphere you have some aggregation models. So we want to couple these two different aggregation models on the double sphere. Okay, so the question is how to couple these two aggregation models, consensus models, in a weak manner. So the crucial idea was given by the Max Lowe 2 years ago in this paper, appeared in Physica D. Okay, so his idea is if you have a different sphere, each sphere you have a different same type, but the size are different. So then if you have the same number of particles on each sphere, so you have an n particle here, you have an n particle here, and then the coupling originally you have this constant coupling strength, the uniform constant coupling strength. So the Lowe's idea is to replace this uniform constant coupling strength by this guy. Here, the bracket is the just inner product in Euclidean space. So you just replace the uniform coupling strength by this time-dependent, state-dependent coupling strength. So the resulting model is this. Okay, so in this way, that's why I call the weak coupling, because the main interaction part the same, but the only difference is we just replace the uniform coupling strength kappa by this guy. Then you can check that this double sphere is the positively invariant set under this dynamic system. Okay, so that means once your initial state lies on this double sphere, then your solution stays there. Okay, so this double sphere is a positively invariant set for this dynamic system. Okay, so that's the key idea. Then by using fortunately, this coupled system can be written as a gradient flow. So if you define the potential in this way, then given this Lowe double sphere model can be written as a gradient flow in this way. Okay, so you take just a gradient in Euclidean space and you project to the tangent space of the sphere. So, and also notice that this potential is analytic. So if you have a gradient flow with analytic potential, then as long as your solution is bounded, it should converge. Okay, so that's the well-known result for gradient system with analytic potential. So, but our double sphere, our state space itself is a compact set. So therefore, boundedness is just given for free. So therefore, you can show that your state, each state configuration converges to some equilibrium state. Of course, we don't have any information about this equilibrium state by using this approach. And also, we don't have a convergence rate of this state to the equilibrium. So that's the weak point. But we know that it converges to some equilibrium, but we don't have any other information, decay rate or the structure of the equilibrium, etc. But just in case, this omega I call the natural, this free flow, if the free flow parts are the same, in that case, we can show that under certain well-prepared initial data, OUI and VI aggregate each other. So you have this complete segregation of two particles. Okay. By using this gradient flow approach, then you can couple finite many Lowe sphere model, swarm sphere models. So if you have n, say for example, if you have n spheres, n different spheres, but then by using this gradient flow approach, then you can couple these n different consensus models on each sphere. Okay, so that's just a slight generalization. And also, if you have a Lowe matrix model, this is a so-called the Lowe matrix model, then you can couple these two Lowe matrix model in weak sense, in weak way, by changing this coupling strength by this state-dependent one. Okay, here F, this is the Frobenius inner product. Okay, so U free, that's F means you take U transpose and free, take a trace and take square root. This is also called the Frobenius norm. And by using this gradient flow approach, and you can also study some emergent dynamics for, and also you can extend it to the multiple Lowe matrix models, not only just two, you can take them as finite many as you want. And also you can do this systematically is by using some algebraic method. I'm not going to talk about this algebraic, this abstract stuff, but because it's almost impossible to explain in short time. But by using this weak coupling, you can also couple the swarm sphere model together with the Lowe matrix model. Okay, so now you have your state, one particle state space is this guy. Use of this, the D by D unitary matrix group. Okay. So as a special case, we can also weakly couple the Kuramoto model with the swarm sphere models, etc. So we have discussed the part of the ongoing story for weak coupling of multiple Lowe tensor models. But so far, our weak coupling only works for the equal number of subsystem size. So if you have the same number of particles in each sub-ensemble, and also the same coupling strengths. Originally, you have the same coupling strengths kappa, then you can weakly couple the given consensus models. But in general, still we don't know how to couple two different consensus models. And also, if you are interested in more systematic presentation, let me refer this recent preprint on algebraic approach for weak coupling of multiple Lowe tensor models. It is available on the archive now. Okay, so let me jump to the last episode. Okay, so let me try to finish as soon as possible. So the last one is the second order consensus model with bonding force. This is a joint work with my Hyunjin Ahn, Dr. Hyunjin Ahn, and two graduate students. The motivation is as follows. So you probably have seen the drone show in many Olympic Games, in particular the Winter Olympic Games. And so you have this drone show. These are all drones. So in order to, of course, this drone show was operated by the so-called centralized control algorithm. So some controller control each drones. But if you want to have some decentralized control algorithm, then we need to use the consensus protocol. And also you see this air show out there, and also the fireworks. Of course, I'm not so sure whether these fireworks can be done by drones, but theoretically, it can be done by this group of drones. So that's the motivation. So I want to do some formation control. So for given a Cucker-Smale model, I want to design some bonding force, so that eventually I want to make this kind of pattern formation by using this Cucker-Smale with the bonding force. So if you can derive such a model, then I want to show under what condition or system parameter, for example, n, the coupling strengths, and the psi, whether the proposed consensus model with the bonding force can exhibit collective behaviors to make sure collision avoidance and the formation control. Okay. So the formal heuristic, the modeling idea is I want to design some bonding force Fij, Fji, so that this resulting system exhibits some pattern formation, some formation. So this try was done 12 years ago by myself and my two collaborators from the engineering school of Seoul National University. The paper was published in the IEEE TAC in 2010. So our idea is to design this bonding forcing term so that, for example, Dij infinity is the desired relative distance. Okay, this is our target desired relative distance. Rij, that's the this guy. This Rij is this relative distance between two the particles. Okay, so I want to design this displacement asymptotically tends to 0, and the speed, the velocity also tends to 0 eventually. So eventually all particles approach to desired relative distance configuration. Okay, so let me just skip this technical derivation, but eventually by using some mechanical idea, our bonding force looks like this. Okay, so first of all, this guy is the Galilean invariant. So because if you just translate the position with the same quantity, it cancels out. Okay, so the total momentum will be conserved. Okay, because you have a translation invariance, therefore you have the linear momentum will be conserved. And also you can have energy. You can have some energy. For example, this is kinetic energy. It's like a bonding energy, like a harmonic potential. If you don't have this, this is exactly harmonic interaction potential. Then by using this direct estimate, this energy, total energy, satisfy this energy dissipation, energy relation. Okay, so you see that this total energy production functional is always non-negative. Okay, so it has a good structure. You have energy dissipation, you have a Galilean invariance, so the total linear momentum will be conserved. So, so under some good conditions, for example, initially there is no collision, and the coupling strength kappa 2 is sufficiently large, and then you can find the positive and lower bound for relative distance. Okay, so in particular, you don't have the positive lower bound, so there will be no collision under this setting. Okay, so initially there is no collision. Then if you take a coupling strength kappa 2, which is given here, this guy. So if kappa 2 is large enough, then you can guarantee that there will be no collision at all. So if there is no collision, although the right-hand side contains the singular term here, but as long as there is no collision, then you can still use the standard Cauchy-Lipschitz theory to guarantee the global existence of the smooth solution. Okay. By the way, for the Cucker-Smale model, this collision avoidance was studied by Cucker and Dong and Jose Carrillo here and many other peoples. Okay. And then by using this energy estimate, so from energy estimate, you can obtain this uniform estimate. So as long as psi can be guaranteed bounded away from zero, then you might want to tell you that this guy tends to zero as t equals infinity, but you need to show that this integrand is uniformly continuous. So once you have a uniform continuous integrand, then by using Barbarat lemma, you can show that this integrand tends to zero as t equals infinity. Okay, so that's the so by using this energy estimate, you can show that the asymptotic flocking emerges, and also if initial total momentum is zero, then each velocity tends to zero asymptotically. So that means asymptotically kinetic energy tends to zero. So the energy converges to some E infinity, because energy is non-increasing and bounded below by zero, so it should converge. Okay, but we don't know whether this E infinity is a zero or just positive number, but numeric simulation tells you for two-particle system, E infinity seems like just zero, but for many-body particle system n greater equal to 3, the E infinity seems to be a positive. Okay, so for special case, the desired relative distance is given by 2r, then even for a four-particle system, the equilibrium configuration is given by these two configurations. Okay, so one particle situated at center, the other one situated this triangle, triangle, or it's like this. So for given n, you have many different configurations. Of course, we don't know whether for given n, whether we have a finite number of configuration, equilibrium configuration or not. That's another interesting question that we don't know yet. The same analysis can be done for the second order Kuramoto model. So you have a Kuramoto model, then by using the same idea, you can address the bonding force there. Again, everything is written as a difference of the phase or frequency. So therefore, the angular momentum will be conserved. And also, this guy has some energy dissipation for certain restricted class of the initial data. So, but eventually the same analysis can be done for this second order model. So let me summarize. So far, we just presented the honeymoon period story. It's a good story only. The collision avoidance, emergence of collective behaviors. However, we don't know whether the relative sorry, this is typo. You have a xi, xj, not this one. Whether this relative distance will converge or not, we don't know the convergence of this relative distance. But for two particle case, we have, it seems to me we have, but for many particle system, we don't know whether this relative distance converge or not. But numeric simulation seems like this relative distance converge. Okay, so let me formalize my talk. So in this talk, we saw that the nonlinear consensus model can serve as a universal model for describing some collective dynamics. And so far, I only talk about the classical model, but fortunately, there is some quantum analog of this whole story, namely called Schrödinger-Lohe model, Schrödinger-Lohe matrix model, Schrödinger-Lohe tensor model. So there is some analogous parallel story for quantum models as well. So if you are interested in this direction, let me refer to this paper. And also now we are working on this some pattern formation using the Cucker-Smale to the moving target configuration. So this one, for example, you have a n bunch of a moving target. So by using Cucker-Smale, this flocking with some extra forcing term, we want to keep track of this moving target. So that's the ongoing work at the moment. So thank you for your attention.
Okay, thank you very much for your talk. Any questions by the audience or people joining online on the chat? Okay, from the audience. Nobody? Okay, maybe let me start with the first question.
Sure.
I don't know if I miss it, but I'm curious, this model where you have the theta hydra and they align all together, can you have the same model, but rather than they all cluster in the same place, you have the theta hydra, you know, their
yeah.
translation.
Right.
Like these models, you know?
You mean this one?
No. It was on the
Yes.
second part. You
Yeah,
have a
yeah.
simulation where all the theta hydra collapsed in the same position.
Position, same position. Yeah.
Uh,
Let me see. 위로 가려면 어떻게? Let me see, just a second.
absolutely.
Yeah. Tetrahedron. Wait, this one. This one. Okay, good. 비디오 보여줘. I mean this one, right?
Exactly. So I was wondering, yes, because they somehow they all collapse in the same place. So I was wondering if with the same type of models or structures, you could have collective dynamics where rather than collapsing into the same place, you will have just the tetrahedra, they will move just to become, say, parallel to each other. So the same up to translation.
Yeah. So far I just talk about this homogeneous ensemble, but so suppose we have a bunch of this tetrahedron, we have a triangle, we have a lines, you have a mixed group, and then your question is whether these lines move together and what this tetrahedron move together and so on, like some flocking phenomena. Yes, that's possible. Yeah.
Okay, thank you. Any more questions by the audience? Maybe just one more question, because it's not clear to me. You have all these unitary matrices and you have the complex numbers, So
Right.
the fact that you use complex numbers, you know, do you exploit this structure somewhere, or is it important for these models? And, you know, I don't see where do they play a role.
Oh yeah. Of course, so far these well-known models is only for the real tensors. Okay, it's not necessarily the complex tensors, but if you reduce from the lower matrix model, which is the unitary matrix, then you can derive some aggregation, some consensus models on the Hermitian spheres in CD, in complex complex Euclidean space CD. Yeah. So well, I don't know how to use this thing, but the special case is the one that we know, this swarm sphere model, etc.
Okay, thank you very much. Somebody came up with more questions in the meantime? Okay, if not, let's thank Professor Ha again. Thank you very much.
Thank you.
Thank you for joining.
Have a good lunch.
Thank you. And actually,
Now, yeah, it's time for me to go to sleep.
yeah, and about lunch.